Hello students, in this video I am going to discuss binding energy. What is the meaning of binding energy, how it comes into the picture, how can we calculate binding energy, how can we compare the stability of the two nuclei, and few numerical examples on the basis of binding energy. So we are going to discuss all these things in today's lecture. So today's topic is binding energy. Binding energy. What is the meaning of binding energy? First question arises, what is the meaning of binding energy? Binding energy can be explained in two ways. Binding energy can be explained in two ways. Suppose we have a nuclei. Suppose we have a nuclei which is strongly bound. Suppose we have a nuclei. We have a strongly bound nuclei. Strongly bound nuclei. And now we want to break this nuclei into constituent particles. We want to break this strongly bound nuclei into constituent particles. So what is our objective? We want to break this nuclei into constituent particles. Constituent particles. For this purpose, basically to break these strongly bound nuclei into constituent particle, we need some minimum energy. We need some minimum energy. So the minimum energy required, required to break a nuclei into its constituent particle. Its constituent particles is known as binding energy. So basically binding energy is the minimum energy that should be provided to the nuclei so that this nuclei breaks into its constituent particles, protons and neutrons. So this is one way to define the binding energy. There is another definition for this binding energy, and both these definition of binding energy gives the same value of binding energy. From both definitions we will get the binding energy. Another definition is for creating, in the creation or to build up a nuclei, from its constituent particles. To build up a nuclei from its constituent particle, Z number of protons and A minus Z number of neutrons. So in this process, when we are building up a nuclei from its constituent particle, an amount of energy is released. Amount of energy is released and this released energy is known as binding energy. So what is the meaning of binding energy? We can define binding energy into two ways. Suppose we have Z number of protons and A minus Z number of neutrons, and we want to create a nuclei by combining these constituent particles together, by bringing these constituent particles together. Then in the creation of the nuclei, some amount of energy is released. And this energy is known as binding energy. Or conversely, if we have a nuclei, we have to provide some external energy to break this nuclei into constituent particles. This minimum amount of energy that is required to break the nuclei into constituent particles is known as binding energy. Binding energy is represented by EB, or sometimes it is also written as binding energy. So binding energy is written as EB or BE. Now next question arises, what is the source of this binding energy? Why this energy is released? When nuclei is formed from its constituent particle, why energy is released? So answer lies, what is the source of this binding energy? So next question is source. Answer lies in energy mass relation. Answer of this question lies in energy mass relation. So when this energy is released, in this process, it means some mass will be lost. Or you can say some mass will convert into energy. So when we are forming a nuclei from its constituent particles, then some mass of the constituent particles, delta m, that will convert into energy, corresponding to this mass energy formula, delta E equal to delta mc square. So in this process of formation of nuclei from the constituent particles, whatever mass is lost, that mass is known as lost mass or mass defect. This is known as mass defect. So when nuclei is formed from its constituent particles, some mass is lost, and this lost mass is known as mass defect. So basically here, this is the binding energy. This is EB. This is the EB energy release. So energy released will be equal to corresponding to mass defect. Multiply this mass defect by C square, we can find out the binding energy. How can we write down the formula of binding energy? Suppose we are forming a nuclei. Nuclei is given by ZXA. Suppose this is the nuclei. So binding energy, what will be the binding energy? Binding energy will be, what will be the binding energy of this nuclei? Suppose we have the mass of the atom. Actually, when we are using different spectroscopic techniques, in these spectroscopic techniques, you will find out the mass of the atom. Rather than finding out the mass of the nuclei, mostly you will find out the mass of the atom. So first we will write this binding energy in terms of mass of the atom, and later on I will convert this formula in terms of mass of the nuclei. So binding energy is equal to the mass of the constituent particles. Suppose mass of the proton is mp, so this is Zmp, plus number of neutron will be A minus Z into mass of the neutron. There will be Z number of electrons in this atom, ZXA, so plus Z times mass of electron. So these are the constituent particles of the atom. If we subtract the mass of the atom. Then this will give me, then this term, this will provide me the lost mass. This will be delta M. This will be delta M. So what is delta M? Delta M is the mass of the constituent particles, or mass defect is equal to mass of the constituent particles, Z number of protons, A minus Z number of neutrons plus Z number of electrons, minus mass of the atom, which we can obtain experimentally by using some spectroscopy, mass spectroscopic technique, and then multiply this C square. So this is the expression of binding energy in terms of the mass of the atom. So here, this is mass of the atom. And this atom is its Z number is the atomic number and A number is the mass number here. Now I want to convert this formula in terms of the mass of the nuclei. Suppose in a numerical they are providing you the mass of the nuclei, then how will you write this formula? That is simple. This will be Z times mass of proton plus A minus Z mass of neutron plus Z times mass of electron, and atom is made up of nuclei and electrons. So I can write it as mass of nuclei minus mass of, this will be mass of electrons. So basically atom is made up of nuclei and electrons. So I have written mass of the atom as the sum of mass of the nuclei and mass of the electrons. So here this masses of the electron will be cancelled out, and our formula will be Z times mass of proton plus A minus Z mass of neutron mass minus mass of the nuclei into C square. This is the expression of binding energy. So in this way, by using either this formula, if mass of the atom is given, then we will use this formula, and if mass of the nuclei is given, we will use this formula. So these are the two formulas to calculate the binding energy. What is the advantage of binding energy? What is the advantage of binding energy? What information binding energy provide us? Basically, binding energy provides us the information about stability of the nuclei. Stability of the nuclei. Binding energy of a nuclei provides us about the stability of the nuclei. If, number one, if binding energy is greater than 0, if binding energy is positive, it means nuclei is stable. It means nuclei is stable. Nuclei is stable. You have to provide some external energy. You have to provide some external energy to remove a nucleon. This is an important thing. If binding energy, first we will calculate the binding energy, and if binding energy is positive, it means if we want to disrupt the nuclei into its constituent particles, we have to provide energy from the outside. This is the meaning of this positive binding energy. Second, if EB is less than 0, it means this binding energy is negative. It means nuclei is unstable. Nuclei is unstable. Nuclei is unstable. And it will disintegrate of itself. Later on, to find out the stable configuration, it may disintegrate. It may disintegrate. Integrate itself. Because its binding energy is negative. What is the range of binding energy? Binding energy, rough range of binding energy is from 100 MeV to 1800 MeV. This is from 100 MeV to 1800 MeV. Roughly, this is the range. This is for carbon and this is for uranium. So this is the rough range of the binding energy for different nuclei. So basically the advantage of binding energy is that it provides us information about the stability of the nuclei. If binding energy is positive, it means nuclei is stable. If binding energy is negative, it means the nuclei is unstable. So this is an important thing that we can find out with the help of the binding energy. Now we are aware that binding energy is suppose positive. It means the nuclei is stable. Suppose we have large number of nuclei and we want to find out that which nuclei is more stable. Suppose 4 or 5 nuclei are given and we have to find out, okay, tell me which one is the more stable nuclei. We cannot compare their binding energy. We cannot compare their total binding energy because that will not give us any information. Because size of the different nuclei will be different, so we cannot compare their binding energy. One nuclei can have 10 nucleons, another nuclei can have 50 nucleons. How can we compare these binding energy? Comparison is always in equal. Comparison is always in between equals. So we have to find out some way in which we can compare two nuclei for their stability. So for this, a term is used to compare the stabilities of different nuclei. The term that is used is known as binding energy per nuclei. Binding energy per nucleon. Binding energy per nucleon. So next important term is binding energy per nucleon. So to compare the relative stability of two nuclei, we will use a new term that is known as binding energy per nucleon. Binding energy per nucleon. What is binding energy? Binding energy per nucleon. Binding energy per nucleon means total binding energy of a nuclei, total binding energy of a nuclei divided by total number of nucleons. Total number of nucleons. So by using this formula, we can easily find out. We can easily find out the binding energy per nucleon. So binding energy per nucleon is, to calculate binding energy per nucleon, first we will calculate the total binding energy of a nuclei and divide this by a number. Divide this by a number. What is this total number of nucleon? So this is total binding energy divided by a number, mass number. Mass number is equal to number of protons plus number of neutrons. So mass number will provide us total number of nucleons. Total number of nucleons. So in this way we can calculate binding energy for different nuclei. After calculating the binding energy of all, binding energy per nucleon for all the nuclei, if we plot a graph between if we plot a graph between binding energy per nucleon as a function of mass number, A number, then we find out this type of plot. If we plot a graph between binding energy per nucleon, here we have binding energy per nucleon. This will be in MeV. This will be in MeV. As a function of A, mass number, then we find out this type of plot. Then you will find out this type of plot. This is a smooth one. I'm drawing the smooth one, and here on the lower side of A, you will find out few peaks like this. You will have this type of plot. So this is the plot between binding energy per nuclei and A number, mass number. Mass number. What are the properties of this? What are the properties of this plot? So first important observation from this, is these peaks. These peaks. It means for few nuclei, these peaks are representing that few nuclei have binding energy higher than their neighboring nuclei. So basically these peaks are representing the nuclei which have higher binding energy per nucleon as compared to the neighboring nuclei. So there are 3 nuclei like 2He4, 6C12 and 8O16 and 8O16. 8O16. These are the nuclei which have higher binding energy. Higher binding energy per nucleon as compared to neighboring nuclei. As compared to neighboring nuclei. As compared to neighbors. This is first of the observation. Second observation is that binding energy for the lower value of A, you will find out first binding energy increases. First binding energy is consistently increasing and it is achieving a peak. And then it is decreasing. Then it is slowly decreasing. So first binding energy is increasing. Here in this region binding energy is increasing and it is forming a broader peak. So first binding energy per nucleon is increasing. It achieves a peak here. It achieves a maxima. It achieves a maxima. At this maxima, which nuclei is present on the maxima, or you can say binding energy is maximum for which nuclei? This is for Fe56. This peak is corresponding to Fe56. And for this Fe56, binding energy per nucleon is 8.8. Binding energy per nucleon for Fe56 is 8.8. So binding energy per nucleon for Fe56 is 8.8 MeV. 8 MeV. Here, this binding energy per nucleon graph or plot, it makes a broader maxima. Here it forms a broader maxima. And this maxima starts from nearly 30. This maxima starts from 30 and it is up to 120. Here, this is 120. You can say this is 56, then I should say here we have this 30 and here 120. This is 120. So in between 30 to 120, it achieves a maxima. So here this is a broader maxima. And average value of this broader maxima. What is the average value of this broader maxima? That is 8.5. Average value of this broader maxima is 8.5. And after achieving this maxima, it starts decreasing. It starts decreasing. Its value around 140, its value, it will decrease and it will achieve, or it will go, binding energy per nucleon decreases up to 7.6. If you find out somewhere here, it decreases up to 7.6. 7.6, this value is 7.6 for 2, this will be for 238. For 238. So when a number becomes, this graph is not properly here, so this scale is not proper. So but you can consider that this binding energy decreases to nearly 7.6 when a value becomes 238. So this type of variation is observed in binding energy per nucleon. So this type of plot is observed. Whatever I have discussed, these are the experimental observations. These are the observations we can make from this type of plot. Now next question is, how can we explain this plot? How we will explain this plot? Next question is, how we will explain this plot? First this is increasing, then this is decreasing. So question in front of us is how to explain this increase and then this decrease. We can explain this type of variation. We can explain this type of variation on the basis of liquid drop. Basically we can compare the nuclei with a liquid drop, and on the properties of the liquid drop, we can explain this. What are the properties of the nuclei? Of the spherical drop, it is spherical in shape. It is spherical in shape and there is a force that is known as surface tension. Due to this surface tension, this liquid drop will achieve the spherical shape. And in between the molecules of the liquid, there is a cohesive force. There is a cohesive force. Similar situation is here. Here our nuclei is more or less of spherical shape, and in between nucleons, protons and in between neutrons, there is a force that is similar to cohesive force is attractive force, and here in between neutron and proton there is a nuclear force that is acting. That is also an attractive force. This is also an attractive force. So in between protons and neutrons, there is an attractive force that is acting. Now first we will consider this. The increasing part of binding energy per nuclei curve for lower values of A. How will you explain? You can explain with the help of liquid drop. We are aware that suppose this is a liquid drop, and these are different molecules of this liquid drop. These are different molecules of the liquid drop. You are aware that it is easy. It is easy to remove a molecule on the surface. It is easy to remove a molecule molecule present on the surface. Present on the surface. It means if we want to remove a molecule present on the surface, we have to provide lesser amount of energy. While it is difficult to remove a molecule which is well inside, it is difficult. It is difficult. It is difficult to remove a molecule which is present well inside. It means binding energy. So we have to provide lesser amount of energy if we are removing a molecule from the surface. So binding energy of the molecule which is present on the surface is less. While binding energy of a molecule which is present well inside the liquid drop, that is large. You have to provide larger amount of energy. Similar thing is happening in the nuclei. If size of the nuclei is small, if size of the nuclei is small, so similar type of thing is here in case of nuclei. And if size of the nuclei is small, then what will happen? Most of the nuclei will be on the surface. So most of the nuclei will be on the surface. So here you are observing that only one nucleon is well inside, other nucleons are present on the surface. So it is easy to remove this. So it is easy to remove nucleons present on the surface of the nuclei. Because it is easy to remove these nucleons on the surface, it means these molecules are reducing the binding energy. These molecules are reducing the binding energy. When they are reducing the binding energy, it means for the nuclei in which most of the nucleons are on the surface, binding energy per nuclei will be very less. Binding energy per nuclei will be very less. As we move, as we increase the value of A, then you will find out a nuclei like this. And you will find out now large number of nucleons are well inside the nuclei. So you will find out when the A number is increasing, you will find out large number of nucleons. This nucleon, this, they are well inside. And their binding energy is high because it is difficult to remove them. Or you can say surface to volume ratio is changing here. Or surface to volume ratio is here. Most of the nucleons were on the surface, so binding energy was less. But here, large number of molecules are well inside and binding energy for them is large. So total binding energy is increased. So as we are increasing the A value, more and more nucleons will be well inside. As a result, total binding energy will go on increasing and average binding energy or binding energy per nucleon will also increase. So due to this reason, for the lower A values, as we are increasing the A value, our binding energy is going to increase. Because as A number is increasing, more and more nucleons will be well inside. Their binding energy will be high, so as a result, average binding energy will increase. As a result, average binding energy will increase. Due to this, binding energy per nucleon is increasing for the lower values of A. For the lower values of A, binding energy per nucleon is increasing. So this is the first part. Now come to the second part. Why this binding energy per nucleon is decreasing? The reason for this is, when we are increasing A, when you are increasing A, what is happening? When you are increasing A, number of protons is also increasing. When you are increasing A value, number of protons are increasing. These protons are positively charged. Positively charged. So as their number will increase, as the number of protons will increase, then Coulombian repulsion between them, then electrostatic repulsion will also increase. So as A number is increasing, number of protons is increasing. Protons have positively charged particles, so in between proton and proton, repulsive force will increase. This repulsive force, electrostatic repulsion, is disruptive. This is of disruptive nature. Because this is of disruptive nature, it is working against the binding of the nuclei. So this is reducing because of the disruptive nature of electrostatic repulsion. This is reducing the binding energy. So as we are increasing the A value, more and more nucleons will be well inside, so binding energy is increasing. Binding energy per nucleon is increasing. But at the same time, this repulsive force is also increasing. And this repulsive force is responsible for the disruptive nature. And this disruptive nature will result in the reduction of binding energy. So up to this point, this surface effect is more important. And after this Fv, this electrostatic repulsion becomes more dominant, as a result of which the binding energy per nucleon decreases after Fe56. So in this way, we can explain this. In this way, we can explain this. Now, on the basis of this graph, we can also explain nuclear fission as well as nuclear fusion. On the basis of this, we can explain nuclear fission as well as nuclear fusion. What is the meaning of nuclear fission? What is the meaning of nuclear fission? Nuclear fission. Nuclear fission means an unstable nuclei having large A value. Unstable nuclei, suppose A is an unstable nuclei. This is unstable nuclei. Unstable nuclei with large A value. A value. It splits into two nuclei which are more stable. This will split into two nuclei, suppose B and C. So, unstable nuclei with large A number here, it will split into two nuclei B and C, which are relatively more stable. Which are more stable. Which are relatively more stable. They are stable nuclei. And in this process, large amount of energy is released. Large amount of energy is released. In this process, large amount of energy is released. Now, on the basis of this plot, I can explain you why this large amount of energy is released. Suppose we have a nuclei here. Suppose I have a nuclei A. Here I have a nuclei A. This is a nuclei A. And binding energy for this is 7 MeV. I'm assuming just. So this is 240. Here, this is 240. Suppose, or 250 here. So I'm saying that we have a nuclei of A number 250 and its binding energy is 7 MeV. So what will be the total binding energy of A? What will be the total binding energy of A? That will be 250 into 7 MeV. This will be the binding energy. So this will be 1750 MeV. This will be 17. So total binding energy of this nuclei A will be 1750 MeV. Now it splits into B of nearly equal A number. So suppose B is somewhere here. One is near to 120 and another is here at 130. Another is corresponding to 130. So this is, suppose one is 120 into plus this is 130 into. Suppose binding energy of 120 is here. 120 is here. So I am saying this is nearly 8. This is nearly 8. Okay. And this is, suppose plus C, this is 130 into 7. It is, this is 7.5. This is 7.5. This is 7.5. So calculate what is the total binding energy. Calculate what is the total binding energy of the deuter nuclei. So here you have to calculate the binding energy of deuter nuclei. Calculate this value. What is the binding energy of deuter nuclei? करिए बेटा जरा कैलकुलेट करिए कितनी होगी. So calculate. So this will be 960. This will be 960 MeV. And this will be 75 into 13. This will be 579. So this will be 975 MeV. So here total energy will be 5 and this will be 1935 MeV. So for the parent nuclei, binding energy is 1750 MeV, while for deuter nuclei, this is 1935. So there is an increase of binding energy. So here, there is an increase. There is an increase in binding energy. And this increase in binding energy will be responsible. This increase in the binding energy will be responsible for the energy released. Energy released will be delta Q. This will be binding energy of deuter nuclei of B plus binding energy of C minus binding energy of parent nuclei. This will be the energy released. How much energy will be released? Sum of these two is 1935 MeV and this is 1750 MeV. So this will be 5 here. This will be 5 here. This will be 13 minus 5. This will be 8 and this will be 1. So 185 MeV energy will be released in this process. So in this process, 185 MeV energy. So you have to remember whenever there is an increase in binding energy, means energy on the right hand side of the deuter nuclei is higher. Binding energy of deuter nuclei is higher as compared to parent nuclei. Energy will be released. So whenever binding energy increases, it means energy is released. Energy is released. And whenever binding energy decreases, energy is absorbed. Energy is absorbed. Absorbed. Why this energy is released? Basically, we can understand from here, when A nuclei is formed, when this A type of nuclei is formed, total energy released will be 1750. This is the meaning of binding energy. When this A nuclei will be formed, this much amount of energy should be released. When B will be formed, then this much amount of energy will be released. When C will be formed, this much amount of energy is released. So when B and C nuclei are formed, total 1935 MeV energy will be released. Now A is converting into B plus C. So when A was formed, this much amount of energy was already released. But when it will convert into B plus C, then total energy released should be 1935. So much amount of energy is already released. So how much energy, total energy will be released here? How much extra energy it has to release for this process? This will be the difference between two. So 185 MeV energy will be released. So what is the formula for binding energy or energy released? What is the formula for energy released? So general formula for energy released or delta E is binding energy. You have to use this of daughter nuclei. Either they can be one, daughter nuclei can be 2, 3, 4 like this. Of daughter nuclei minus binding energy of parent nuclei. Parents, daughters, nuclei minus. This is the formula for calculating binding energy. So in this way, we have shown that in case of nuclear fission, a large amount of energy will be released. A large amount of energy, roughly 200 MeV energy will be released when nuclear fission is taking place. Now consider the case of nuclear fusion. We can also explain nuclear fusion from here. Nuclear fusion. For nuclear fusion, what is the meaning of nuclear fusion? In case of nuclear fusion, we have two nuclei whose A number is less. They fuse together and form a heavy nuclei, C. Suppose we have a nuclei here whose A number is 10, and I'm considering another nuclei whose A number is 30. So I'm considering two nuclei, A number 10, mass number for this is 10, and for this 30. So this will become 40. This will be C40. So 10 into, suppose for this 10, binding energy per nuclei is 3 MeV, plus for this 30, this binding energy is, suppose, 5 MeV. So this will be 30 plus 150. So this will be 180 MeV. So this is the binding energy of parent nuclei. This is the binding energy of parent nuclei. Now for daughter nuclei, this will be 40 somewhere here. So this will be nearly 6. For 40 nuclei, this is the C nuclei. Here this is A nuclei. This is B nuclei. For C nuclei, this is 40. And suppose this is 6. So this will be 240 MeV. 240 MeV. So what will be the energy released? So how much energy will be released here? This will be the binding energy of C minus binding energy of A minus binding energy of B. So this is 240 minus 180. This will be 60 MeV. So in this case, 60 MeV of energy will be released. So this is the case of nuclear fusion. Nuclear fusion. In case of nuclear fusion, two lighter nuclei combine together, fuse together to form a heavy nuclei. And as a result of this process, large amount of energy will be released. 60 MeV energy is released. So in this way, we can explain this plot. We can explain this plot, and on the basis of this plot, we can again explain nuclear fusion as well as nuclear fission.